Good morning, everyone. We are still continuing our electromagnetic induction classes. And yesterday's class, we dealt with dynamically induced EMF, and I mentioned statically induced EMF. Yesterday, what we concentrated more was on dynamically induced EMF, which means that a conductor is moving, dynamic conductor is moving within a stationary magnetic field. We saw the equation BLV sine theta, and we did a small problem on that. Continuing with that in a small bit, I just wanted to mention something about magnetic damping, which is not directly there in your syllabus, but still I would like all of you to know about it. Just a mention, small mention. Okay. So this was what we did yesterday. So today we'll go on to this itself so yesterday when we discussed about dynamically induced EMF, we said if you have a north pole and a south pole, and if you move a conductor within this, an EMF is induced. Now let us see, instead of a conductor, if I am using a solid core, it's a surface area, it's a solid core, a solid core, not a conductor. It's not a conductor. This is a coil. This is not what I'm going to use. Instead of the coil, I'm going to use a solid core. Okay. And if I am moving this core inside, I know there are magnetic lines of force like this. And if I'm moving this inside, of course, because the solid core is encountering a change in magnetic flux, because when it going inside, it is going on increase. The magnetic flux is going on increasing. When it moves out of the magnetic field, the magnetic flux is going on decreasing. The magnetic flux linked with the solid core is going on increasing and decreasing, of course. As a result of which, a current should form, isn't it? As a result of which an EMF should be induced, and as a result of which EMF will be induced, and induced current will also flow. But how does that current flow? Because it is a solid core, currents flow within this, okay, within the core, okay? Currents flow like this. It forms small loops within the core. Lenz doesn't like it. Whenever there is a change in magnetic flux, Faraday is happy. But Lenz doesn't like it. Lenz says, no, I will not permit a... No, I will not. No, according to Lenz's law, the magnetic flux should not change. So what happens is that some small current loops will be formed within the core, and these currents will be flowing in such a direction as to produce their own magnetic flux, which will be opposing this change in magnetic flux. Which means whenever it goes in, what is the very cause producing this induced EMF? The movement of the solid core this movement within the magnetic field. So when it enters the magnetic field, it gets slowed down naturally. The entire phenomenon is opposing that movement towards the magnetic field, and when it goes out of the magnetic field, it is opposing that, so it speeds up later on. Or in effect, within the magnetic field, you have something known as a slowing down, or you call it as magnetic damping. Magnetic damping occurs, or magnetic braking occurs. A solid core, even if it should be a free flow. Suppose you are asking a pendulum to move within the magnetic field, the pendulum will find it gets slows down, and once it moves away from the magnetic field, it again becomes faster. Again, when it comes down, it comes fast, but within the magnetic field, it slows down, and then it goes up. All because of this electromagnetic induction and these currents, and as a result of which there is a opposition to this movement. This is called magnetic damping. And what are these currents known as? I hope you all remember, these currents are known as eddy currents. Eddy currents. Now, eddy currents bring in eddy current losses. You will learn about it later on also. Losses, and eddy current losses bring about lot of heat also. Or you can even say that this kinetic energy, you always think about energy conservation. This kinetic energy, this movement, when it gets converted into heat, kinetic energy is reduced, or the heat is produced at the expense of the kinetic energy. The heat produced within the core is at the expense of the kinetic energy. That is why the kinetic energy slows down, and after the magnetic field is over, it increases. Now, the importance of magnetic damping is that this kind of damping can be used wherever you want contactless braking. If you want to slow down some surfaces where you don't need contacts or contactless, which means frictional losses, all those losses are lesser. You don't want two surfaces to rub with each other. In such cases, you can use magnetic damping, and or you will find that in later stages in your curriculum, you'll find there are many things like hunting and all those things happening in a machine, etc., where deliberately eddy currents are being introduced, or you want eddy currents to flow so that magnetic damping is occurring. Now, if you want, suppose inherently you are deliberately put this, but there are cases where you don't want eddy current loss to happen. In such cases, what you do is, in the solid core, you will try to, the solid core, you will try to reduce the eddy currents are occurring because currents flow in like this. They form their own paths like this. What you can do is you can break these by instead of the solid core, you can have a core like this. You can have a core with with slots like this, okay, like this and all, or put lamination, etc., so that the currents they will find it hard to make long circuits, or the eddy current. So this is not possible because it is air there. So the eddy current, the circuit through which the eddy current flow will be reduced, which means the eddy current as such will be reduced, and the eddy current heating losses also gets reduced. You will find that later on, you will find that many cores of many machines, electrical machines, are laminated. Laminated means the core is not a single core like this. It will not be a single core like this. This core will be made up of small sheets which you keep together. Within and in between the sheets there will be varnish, etc., so that had it been a single core, then eddy currents can form like this, okay, like this. But if you form the core by using a number of sheets kept together, the eddy currents will find it hard to move, to form larger circuits. So, and the eddy currents will be lessened. So there are cases where you want eddy currents or to flow, as in the case of magnetic damping. There are cases where you don't want eddy currents to flow. You want to reduce the eddy current losses, wherein the cores of the machine will be laminated, as in the case of transformers, as in the case of generators, etc., where you have a large core. The iron core or the magnetic core will not be a solid core, but laminated. That is one thing that I wanted to tell you today. One thing, as electrical engineering students, I think you should know this. Another thing is that whenever you have an induced EMF, see, P is equal to power. Power is equal to voltage into current, okay, or the induced EMF into current, induced into current, say. Now, this is also equal to I squared R. As you very well know, I squared R is the power, or the energy will be I squared RT. So, which means this is in it's in watts. Isn't it? Power in the unit is watts. This is the same as joules per second. Same. Watts and joules per second are the same. which means that joules, whenever you come across joules, it means it is related to work done, isn't it? So someone has to do a work here. Someone has to do work, isn't it? In order to produce induced EMF, in order to produce power, in order to produce the electrical energy, somewhere someone has to do work, isn't it? Who is doing the work? The coil has to be rotated within the magnetic field, or a magnetic field, north and south pole, has to be rotated within a container, within a core where you have many conductors. So someone has to do work. Anyway, it has to be rotated. It has to change its position. That energy is being supplied by fossil fuels. If it is a thermal power station, you use coal, or you have to burn oil, as in the case of diesel power stations, or you have hydro, as in our Idiki, hydropower, the water power or water head is being used, or you can have wind turbines. So these are the things, these are the persons, or these are the sources which do work so as to rotate the coil or the magnetic field, or so as to bring in the change in magnetic field so as induced EMF is produced. This is how you have a diesel power plant, or you have a thermal power plant, or a hydro power plant. Each one of these portions are, what are they doing? They are effectively doing that work so that induced EMF is produced. So this much regarding our dynamically induced EMF, where the conductor is moving. Now, we are going to another portion where statically induced EMF means what? You have conductors are kept in the core. Now, in a electrical machine, what happens is, I don't have anything else here. So you have a core, and the machines in a DC machine. I'm talking about a DC machine. A DC machine, you have the magnetic field here, and you will have a core where this core will have the conductors, and the conductor will be moving within the magnetic field. There will be an air gap. In the other case, that is, if it is an AC generator that you're speaking about, AC generator has coils kept here. Coils are stationary. Coils are kept here, and within that coil, you have magnetic field, magnets made of magnets which are electromagnetic in nature, or permanent magnets. They will be rotated like this. When they are rotated, it is effectively changing the magnetic field. So that is statically induced. Another mechanism is, if you have, say, a coil, okay. Let me go to this representation later. Suppose I have a coil through which I pass a current, okay. And when I pass okay, let me put it as just a coil here. Coil. I have a coil through which I pass a current, and which is varying in nature, okay. Which is varying in nature, which means I have a magnetic field produced. Whenever I pass current through a coil, I have an electric field as well as a magnetic field. Okay, whenever I pass a varying current through the coil, I get a varying magnetic field. Now, this varying magnetic field is linked with the coil itself. Ee coil linked on. And when the magnetic flux linked with that coil varies, an EMF is induced in the coil also, isn't it? So today, what we are going to learn is quantify the ability of a circuit to fight the magnetic flux produced in that circuit itself. ഇതിനെ ക്വാണ്ടിഫൈ, അതായത് ഈ കോയിലിൽ കൂടെ ഇൻഡ്യൂസ്ഡ് EMF ഉണ്ടാവുന്നുണ്ട്. When you pass a varying current through a coil, the coil experiences a change in magnetic flux within itself, and induced EMF is produced. So coil will be opposing. By Lenz's law, the coil has to oppose this. This opposition, this fighting capacity of the coil against the change in the magnetic flux is called as self inductance, which you normally denote by L. So L is nothing but the coil trying to oppose the magnetic flux variation in itself. That is called self-inductance. So we all know, now let's now try to get some expressions for in that self-inductance, and that is all that we'll do today. So suppose I have a coil and I'm passing varying current through it, so that varying magnetic flux is produced. Then that value, okay, that value, if I put like, usually you put a resistance and a coil like this. This together is a coil, okay. Any coil cannot have a pure inductance. And then I have a switch and I put a DC, or I put a DC source battery. Okay, a current flows. Whenever I switch, put the switch on, the current flows. Okay. Now, when I close the switch, the current in the circuit wants to increase. Okay. When I close the switch, whenever I want to close the switch, the current in the circuit wants to rise. But the self-inductance L says, no, no, no. It's not that easy. I cannot permit you to go on increasing. I will not permit it because I don't like such a change. I am working as per Lenz's law. Okay. So be it an increase or be it a decrease. So self-inductance is fighting the current from changing. Current should not go on increasing. But if you wait for a little more time, finally L gives up and current reaches the maximum. That is why if I plot this value of current with respect to t, if it has a maximum I max, when I switch on, it starts increasing. It fights with L. It fights with self-inductance, fights with self-inductance, and finally self-inductance gives up and it becomes I max, which is V by R. From then on, Ohm's law is satisfied. Ohm's law can be applied, not before. Okay, so L loses the flight. So how much time does it take to reach that? It depends on the time constant, etc., which you will come to about it later on. So I just wanted to make sure that you understand the concept of L. L is nothing but you're quantifying the fighting spirit of a conductor or a coil. The fighting spirit, you're quantifying, you're making the value of, or you're finding out the value of how much fighting spirit does the inductance have, or does the coil have in fighting against the change in magnetic flux, thereby it is fighting against a change in current through it. That is L. Now let us, even if we can say all these things, what really matters is how can you mathematically express it. That's all that we are going to do today. As you all know, by Faraday's law, E is equal to N d phi by dt. That is equal to d by dt of N phi. Okay. Now, this N phi is produced by what? The current, isn't it? When you pass a current through a coil, you get a flux. When you have n number of turns, you have N phi flux. So I can always write N phi is proportional to I. Whatever current I pass through the coil, a proportional flux is produced. Okay, you have to take down these equations. So N phi is equal to I. So I can always write this as E is proportional to I. Oh, sorry, E is proportional to this d by dt of I, isn't it? Instead of N phi, I replace by I, but I have to retain it as as proportionality because N phi is proportional to I. Or I can rewrite this as E is equal to di by dt with a proportionality constant, which I call it as self-inductance. This is my first expression. E is equal to L di by dt. This is called a self-inductance of the coil, and it is expressed in Henry. Henry. And if I have if E is equal to 1 volt, and if this di by dt changes at the rate of 1 ampere per second, then L is 1 Henry. Or I can say that a coil has a self-inductance, or a coil has an inductance of 1 Henry if an EMF of 1 volt is produced or induced in it. 1 volt is induced in it when the current through it changes at the rate of 1 ampere per second. So that is our first expression. E is equal to L di by dt. Now other expressions are also very easy. They come from this. Okay. So first equation, E is equal to L di by dt. So as I am writing the expression for L is equal to E by di by dt. That is my first equation. So one inference from this equation is that L is dependent on the rate of change of current. If the rate of change of current is high, L will be small. If the rate of change of current is small, L will be greater. So that is one inference, one takeaway from that equation. Second equation, E is equal to N d phi by dt, which is as per Faraday's laws of electromagnetic induction, and we also found out that it is equal to L di by dt, which I can modify as d by dt of N phi, which is the same as d by dt of Li, or I can say Li, or I can correlate each other and say N phi is equal to Li, or I get L is equal to N phi by I. Equation 2. Another expression for L. And what is the takeaway from here? The inductance L is dependent on the number of turns as well as flux and I. But one more thing that you have to remember here is that in this case, N is a constant, N is a number of turns, N is a constant. So L is dependent on the ratio phi by I. Isn't it? If you leave away this N, whatever remains is phi and I. So that ratio phi by I is important. If L will remain a constant, if and only if phi by I is a constant. Why do I stress on phi by I? Because phi by I is exactly your magnetization curve, BH curve or phi by I curve. And this phi by I remains a constant only in the linear range. After some point, it becomes saturated. So L, the inductance of a coil, is has a constant value only in this area. That is the linear area where phi and I are, phi and I are proportional, which means phi by I ratio remains a constant, linear area, not in this area. This area is actually a saturation area. So whenever you design an electrical machine, I'm coming back to that. Whenever you design an electrical machine, sorry, I'll stop within 2 or 3 minutes. Whenever you design an electrical machine is usually designed so that the flux density or the flux and all those things that come in that, all those parameters will come in that particular machine in such a way that the flux and I remain constant. They are in the linear region, not in the saturation region. One more thing is that then the analysis is easier. Whenever the system is linear, the analysis of the system is very easy because superposition principle is applicable. But once it goes to the saturation region, it becomes a non-linear system. The analysis is also very difficult. So always it is a dream of a designer to design anything, be it an electrical system or be it any other thing, to design it so that it works in the linear range of the operating parameters, linear range. So what I wanted to stress here is L remains a constant only if phi by I remains a constant. That too, which it happens only in the linear region of the magnetization curve. Magnetization curve means BH curve because flux density B depends on phi and H depends on I. They are the same. Both are the same. Very last equation, last expression, 3, in terms of physical quantities. L is equal to this equation. I'm taking this equation. N phi by I. Now, flux phi is equal to MMF by reluctance. That you know is Ni by L by mu 0 mu r into A. The reluctance equation we have already learned. Or reluctance is S, we usually denote by S. Or now I substitute this equation here and I get L is equal to N squared. This N and this N comes. N squared by I and I get cancelled. Okay, N squared by L by mu 0 mu r into A. Or that is L is equal to N squared by S. So L is dependent on the length of the coil. It's dependent on the permeability, relative permeability. It's dependent on the area. It is dependent, or as such, I can say it is dependent on the reluctance of the coil, which means these are the 3 equations that you have to remember. L is equal to E by di by dt. L is equal to N phi by I. L is equal to N squared by S. This is where I'm going to stop today. Okay. Any doubts or anything that you want to ask me, you can ask. Or if you want to remain and ask me, you can. So that is it for today. This is the... No. Okay. Bye.